Hello, Physics Nation. My name is Nate Larmond, and I'd like to do a few simple demonstrations that you can do at home with a coffee filter, a yardstick or a meter stick, and a backpack with some weight, some heavy things here that I'm going to put in the backpack. Anyway, these demonstrations are all about equilibrium. And coffee filters are great because they're super cheap and they're really precise. They're the same shape, same mass, within really tight tolerances every single time. So this is equilibrium that everybody understands. There are two forces acting on the coffee filter. If we isolate the coffee filter in our mind, if we draw a little system boundary around it, what are the two forces? Pause and think about the two forces yourself. Most students will identify gravity as pulling it down and my hand as pushing it up. Well, in physics class, we have a fancy name for the hand force. See how my hand is horizontal? Yeah, well, the reaction force provided by my hand is called the normal force. Surfaces always push back at a right angle. So if my hand is tilted, the normal force is like this. And eventually, it provides no normal force. If my hand is vertical, it doesn't push at a right angle at all. Anyway, this is called static equilibrium. All right, it just sits there. Gravity pulls down, the normal force pushes up, and if you add the two forces, you get nothing. Okay, this is called static equilibrium. No motion, more importantly, no acceleration. This thing achieves its terminal velocity almost immediately. And the cool thing about coffee filters is you can just open them up a little bit, make their cross-sectional area just a little bit more, and they fall very, very slowly. Hang on. It's really magical motion. It falls at a constant velocity. And that's also equilibrium, except now my hand obviously isn't touching it. So what cancels out gravity? Well, the fluid that it's plowing through. It's plowing through air. Um, I guess you'd call it a dynamic shear resistance force. But the bottom line is it's not accelerating so the forces are balanced. It's called dynamic equilibrium. The downforce of weight is perfectly canceled by the fluid upwards force, and it stops getting faster. It stops accelerating. All right, so that's the one that always trips students up. Students understand that still static equilibrium is a balanced situation. Up plus down gets you nothing. But this takes some thinking. This is called dynamic equilibrium. Even though it's moving, it's not accelerating. So the sum of the forces are also zero. Now I'd like to do some rotational motion. Let me back up just a little bit. Grab a yardstick or a meter stick or a baseball bat or really anything and try to balance it vertically like this. So this system is also in equilibrium. It's in rotational equilibrium, and there are two forces acting on the stick. The weight of the stick itself, you can pretend it's concentrated right there. This is a meter stick, so at 18 inches, you can imagine there is a point mass called the center of gravity of this stick. And the other force is my hand. So this force is passing through the center of gravity, or the pivot, or the fulcrum, so it's exerting no torque. This force also, at 18 meters, is passing through the lever arm. That is, it's perfectly parallel to the lever arm. It's passing through the fulcrum, the axis of rotation. So this is rotational equilibrium. And this is a fun trick to do. As you can see, I could do it all day long. So now what we're going to do is a different version where there is actually a torque, and we're going to fill up this backpack. Let's make this backpack heavy. So here's our physics textbook. College Board did not endorse this video in any way. It's really heavy. It's our workbook. And I'm going to put 12-ounce soda. 12 ounces is obviously 3/4 of a pound. So what does this thing weigh? I have no idea. Maybe 3 pounds? Okay, so let's make my wrist the fulcrum right there. See my pivot point? And then let's apply this force, that is the weight of the backpack, very close. So this is called static equilibrium. Okay, there's my pivot right there. That's the fulcrum. And there's my lever arm, that distance in between the pivot, my wrist, and the applied force. So, I don't know, maybe 7 or 8 inches. So what you do is you take this torque, this is a twisting force. For you on the screen, I guess it'd be negative, right? Because if you do the right-hand rule, it's, I don't know, it's away from you, I think. Anyway, my wrist is applying a opposing torque. My wrist has to twist this thing counterclockwise. And that should be coming at you. That should be a positive Z torque. Use the right-hand rule. There's nothing wrong with clockwise and counterclockwise, but it's actually better to say the backpack applies a negative Z torque and my wrist applies a positive Z torque. Anyway, this is equilibrium. Okay, so the weight of the backpack multiplied by that lever arm is the torque the backpack applies to my wrist joint. And the fun demonstration you can do is just make it go out further. The weight of the backpack has not changed. That's the little puzzle. The force is the same, but now because it's further from my wrist, it applies a much bigger torque, and it doesn't take long before you can't even support it. It applies a gigantic torque. So, like I said, they're fun demonstrations that have to do with equilibrium. This guy is translational motion. This is called dynamic equilibrium. And this is called what? Rotational equilibrium. So gather some fun common household objects, coffee filter, yardstick, backpack, and some weight, and you can surprise and amaze your own family members at home and do some fun pandemic science. Thanks for watching. See you in the next video.